So next speaker is Professor Pravesh Biyani. He's an associate professor at IIIT Delhi. He is a BTech from IIT Bombay and MS from McMaster University. And he also has done a postdoctoral research stint at University of Minnesota, Minneapolis. He is an Inspire Faculty Award recipient of the Government of India in 2012. His research interests lie in the intersection of signal processing and machine learning with applications to urban transportation and speech processing. So he's very passionate about public transportation, and we'll get to maybe hear some of that today's talk. Pravesh?
Yeah, thank you, Geeta. Can you, I hope you can hear me well.
Yes, audible.
Great, thanks. So I can start.
Yeah, do you want the poll now or later?
I think we can start while I introduce, you can give the poll.
Okay, so I'll launch a poll. All the participants can vote, can choose. Do you see the poll?
I can.
Yeah. Okay, the votes are coming in. Maybe you can continue speaking when the votes are coming. Yeah.
Sure. So thanks, Geeta. So I'm Pravesh, and I'm an associate at IIIT Delhi, and I run mobility and optimization lab. And the topic of today's presentation or discussion actually came to me around 3 to 4 years back. And I would like to take what Tal left from the previous presentation. So 3-4 years back, I was working as a consultant for Yatra.com, which is a travel planner, airline travel planner, and we wanted to start a point-to-point bus service for employees. We wanted to build a service that plans routes for point-to-point bus service for employees. And one of the roadblocks that we hit eventually, as soon as we started working on the product, is that we didn't have the traffic data. We didn't have the future traffic data, and we wanted to have bus-specific traffic data. And Google Maps API that time and even now was very costly. It was out of our reach, so we wanted to build our own traffic model, and that is where this idea of traffic and air quality imputation came up that time. So, Geeta, is the poll is maybe
yeah, about 50% have voted. Shall I end it now?
I guess, yeah.
Okay. Yeah.
So
close the
great.
poll.
So,
I'm sharing the results.
nice. And maybe, Geeta, we can have the second poll after 3-4 slides.
Sure.
Great. So this Bayesian matrix completion that I'm going to talk about basically came from my own personal problem that I faced a couple of years back. And I've been working on this problem since 3-4 years. And now with air pollution as another big problem that we need to solve, folks on transportation also has gotten air quality monitoring and air pollution problems. So this method also applies there in air pollution problems. So I'll explain these two problems, and I'll try and very quickly I'll try and explain the problems in 10 minutes. And the second part of the presentation, I'll try and present a method that is not deep learning for a change in AI. So this is, interestingly, these problems are very standard AI problems that are applied in image processing and video processing, but we are going to see their applications in air quality monitoring and traffic imputation. So here is how traffic and air quality data generally look like. Well, it's not how the data look like, but generally.
Pravesh, are you changing slides? Because we are seeing only the first slide.
Oh, yeah, I am changing slides. How do I?
Maybe you need to.
Okay, resume share.
Yeah.
Okay.
Yes, now we can see.
You can see the slide? Okay.
Yes.
I hope you can still see.
Yes. Yes.
Great. Okay. So this traffic and air quality data actually are embedded generally in the map. So you can see on your left side of the screen, there's a map. It's very standard to what you see in Google Maps, except that there are two colors here. There's a blue color and there's a red color. So generally traffic data is like, traffic is like a graph. So you have nodes and you have edges. And what we really want is the speed in the edges. So if I want to go from, one node or one square to the second square, what is the speed of the vehicle that I want to drive, is what the traffic data means. So this is the on the left side. On the right side, you have air quality data, and I'll tell you why these two data have similar characteristics. You have, this is the map of Delhi, and the green icons that you see are air quality monitors installed in Delhi. So there are some 30, 40 air quality monitors that you can see. These are Central Pollution Control Board monitors, and these are monitors installed in Delhi. And you can see that, Delhi is a big city. It's almost a 50-kilometer cross, 50-kilometer grid, and there are not even 50 monitors, industry grade official monitors installed in Delhi. So I'm going to discuss these two problems, and I'll tell you how these two problems are, have a similar characteristic, and how do we solve a problem that I've not discussed yet actually. Sure. So generally, this air quality and traffic data are, space and spatio-temporal data. So they are lie in space. So there is a location and there's a time. So you can have a location as your column, and rows, and time as your columns. So for example, say Connaught Place, you have the air quality changing in that location in Connaught Place, and similarly for other locations. Similarly, for traffic data, you have a street whose speed, of a given mode, for example, a bus or a two-wheeler or a car or a bicycle, the speed of that two-wheeler changes as the time goes. So in the morning you have congestion, in the evening you have congestion, in the afternoon and in the night you don't have congestion. So the speed slowly changes for every location. So the problem that we intend to solve, the problem that we intend to discuss in this presentation is the following: that if I don't have the traffic data for all the streets, if I only have traffic data for some of the streets, and I'll tell you why this is coming to picture again and again. But if I don't have all the traffic data with me, can I extrapolate the given traffic data to get the traffic data of the remaining area? Okay, so if I don't have a vehicle running, if somebody is not giving me the speed of a certain street, then can I get the speed from some other measurement? Similarly, for air quality, if you consider a city as a grid, if I don't have static monitors in all the places, if I don't have monitors in all the places, then can I extrapolate the air quality in those places where I don't have monitors? So this is the traffic problem, this is the air quality problem, and you can see that both these problems have a similar nature, that there's a missing data problem. So you don't have air quality data for all the mohallas, for all the colonies, for all the locations of your city. Similarly, you don't have traffic data for all the locations of the city. Interestingly, Tal in the previous presentation talked about that problem where there's a service provider that is running vehicles. Maybe he has 50 vehicles. Now he has to give expected time of arrival for a vehicle to a certain customer, and doesn't have traffic information for that, or maybe Google Maps or some other APIs are too costly for him. So how does that service use the data, GPS data that is available, the traffic information that is available with their limited vehicles to extrapolate for the remaining city? And similar problems happens in other modes as well. So this is incomplete, and so this is the problem, right? So we have this incomplete matrix, and this is a complete matrix. This is what we want to reach. We want to go from this slide to this slide. So anyway, this is how the system works. What we have done in Delhi, and I'll tell you about the experiment in more detail later, but what we have done in Delhi is we have basically put in GPS in buses, in almost all the public transit vehicles. And these public transit vehicles are basically sending their GPS and their speed information through to a server. And there's an API that is basically fetching that information in form of speed. And this is how we are calculating the graph, the complete traffic data information. So this is generally a sort of an IoT system that is employing what we call as a data science or a machine learning or an artificial intelligence based model to complete the data. Okay, we'll come to that more in the scene. So anyway, so let me just talk about the first problem of two problems. That is, what do we want? What is the objective is that we want a very dense air quality map of a city. Okay, so by that what we mean is we want for every square kilometer, or maybe even 500 meter square, small grids, very small area, we want to understand what are the pollution parameters of that place. So what is PM 2.5, what is PM 10, what is NO2, NOx and SOx density, gas density there, because these are the pollution data. That's what we want. Why do we want that? We want that because if we don't know the local pollution level, will not be able to find the source of the pollution, and therefore will not be able to, reduce the pollution. If we don't know the source, then we can't, go and switch off the source. So therefore, we want a very dense map of pollution, of air pollution. Now, if I want to put static monitors in almost 2,500 locations of a city, or 1,000 locations of a smaller city, let's say, let's say Bhopal or Ahmedabad or Bangalore, then it's extremely costly. And that is the reason why, uh, the government has not been able to put, one of the reasons why the government has not been able to put sensors which are static in the city. Okay. And if we can't measure the pollution at very local level, at a very granular level, then we'll not be able to tackle the problem. We'll not be able to go to the source apportionment of the pollution source. So therefore, building a dense map is costly, but it's very important. So the idea that we came up with is the following: that can we substitute the static sensors, that don't move, with moving sensors to obtain better and cost-effective spatial coverage. So it's something like this: if I know that my two locations, if somehow I know that my two locations have similar air quality measurements, then do I need two monitors? Maybe not. I just need one monitor. I can take this monitor, to location A, and after some time to location B, and then again to location A, and so on and so forth. So basically, I'm going to multiplex my monitor to multiple places. I'm going to use one monitor to monitor multiple places. So obviously, if I'm using one monitor to monitor multiple places, then basically I'm moving that monitor. Okay. So the idea is to take few moving sensors, okay, and take them around in the city and sample the air quality in different places of the city where they don't have static monitors right now. And therefore, what you get after sensing is basically exactly this, is exactly the graph that you saw before. So this is like a static monitor that's going from this location to this location to this location, and so it's sensing various locations and at various time instances. And maybe this is a static monitor that was here, then it went here and here and here maybe. So you're sensing different location from one moving monitors, and then you're trying to, then the question is, can we complete the remaining matrix if I have these partial observations of the air quality data in the city? The question is, why does it even, why do you even think that you can do that? Because the structure of air quality data allows you to do that. Because, and I'll refer to the structure later again in the presentation, but let's just say that there's a redundancy in the air quality data, which means that you don't have to measure everything. If you measure few things, you can extrapolate those few things to estimate the remaining stuff. Okay. So there's a redundancy in the air quality data of a city, and that's not very difficult to see, that locations that are nearby may have okay, correlated pollution data. For example, if there is a source that is polluting two sources nearby, two areas nearby, then obviously the data, the entry of those two points will have a correlation because they're coming from the same set of sources. Okay, so there's a redundancy in air quality data, which means that we don't have to sample everything at every point of time, and therefore you can sense few of them in space and time in a smart and clever manner, and extrapolate for the rest of them. Therefore, you don't have to have static monitors at every place. You can do away with fewer moving sensors. Okay. In fact, our experiments say that, and that's exactly the last point of the slide, that moving monitors coupled with some spatio-temporal extrapolation can save air quality monitoring by 80%, the cost, which basically means that you don't have to have 500 or 1,000 monitors. You can have 50 static moving monitors, and you can still do a good job. Which basically means that we can go to, we can solve the air pollution problem at a very, very local level, which is very important. Similarly, for traffic estimation, again, as I said, is a very important component for routing decisions for ETA. And you can exactly do the same thing for traffic estimation also. For example, a lot of you answered that Ola spends around $100 million a year just in Google Maps. So just to give you a perspective, this number is told to me by somebody from Ola, and I believe that because understanding how Google Maps work, that is reasonable. Basically, they are spending 5 to 6 rupees on using Google Maps service, including directions, including maps, including traffic, and the whole data is basically the Indian data. Talking about Atmanirbharta, right? it's an Indian data, and we are paying like $100 million to Google Maps. Not that it's a bad thing to do, but we have methods that we can employ to also generate our own data and not use Google Maps. So, for example, public transit agencies can use their bus data, their bus GPS data, to do a better traffic estimation using similar approaches, and they can create a better routing and better ETA estimation for public transit. Good ETA in public transit employs more riders. More riders implies better revenue and better service. So with using such data science and AI tools, we can actually improve the service overall. So therefore, the objective of traffic estimation again is to use what we have and extrapolate for what we don't have. So this is the pilot that we are doing right now in Delhi. So this is an auto in the left side. You can see an auto, and here's a traffic air quality, not traffic, air quality sensor that we have built along with our partners from Urban Sciences, and these are Atmos air quality monitors, and this is the battery on the left side, and this is the monitor on the right side. And this auto is then, we have installed the air quality there, and the auto is moving all across Delhi and giving us the data. We are going to install around 10 more monitors soon once the bus service picks up in Delhi in buses, and we are going to report our results on that very soon. So this is something that we in the lab are doing right now. So anyways, so coming to the problem of finding the missing data. So what is that structure that I was referring to? What is that structure that you can leverage to complete the remaining data? Okay, and that structure, the first structure is the low rank structure. So here's a very nice paper by Medlin and Townsend, and they say that why are big data matrices approximately low rank? So they came up with a latent variable model, and they said that look, an M cross N matrix has a rank of that grows with order log of n plus m. Now log of n plus m is a very small number actually. So basically they are saying that if you have 100 rows, your rank may be something like 5 or 6 or 10. Okay, it's a very small number, which means that you don't have to have all the entries. You can employ the low rankness property. You can employ the low rankness structure to fill the whole matrix. That's the main idea. However, our problem has some specifics that we need to understand. First of all, the air quality data or the traffic data is basically online. It's coming online. It's coming sequentially. So the buses are moving, they are sending us data. The autos are moving, they are sending us data, right? And secondly, the columns that you see on arriving, right? So these columns, they are very close to each other. So you can see that there is a very slow variation in the columns. Okay, so that is the second specific of the problem that we have to understand. The third is that we don't know the rank. Even though it's low rank, we don't know the rank. Okay, and even the subspace in which this data lie, the low rank subspace in which data lie, may also vary with time. So the morning may have a different subspace, and the afternoon data may have different subspace. Also, very important in terms of applying machine learning and AI algorithms, we don't have ground truth. Okay, which basically means that we can't apply standard deep learning algorithm just like that. I'm not saying deep learning can't work here, but there's no ground truth available for us, which means that we have to sort of build the model and understand how to impute the data from there. Finally, as it's true with all the data, it contains outliers, and it may also be very noisy. So fine. So we have this problem setting where we have this online data coming to us, incomplete data, online data coming to us, and we want to complete the whole matrix. And the question then, the obvious question is then, why even bother with a new method? Why not apply that has already been done? Standard matrix completion is a very old problem, maybe 20 years old problem, and why can't we use them directly? So the answer is that standard matrix completion generally are not dynamic in nature. They're very static in nature. So Netflix problem does not assume, for example, data with temporal correlation. So there is no temporal correlation generally in Netflix problem. On the other hand, time series forecasting methods do understand the temporal correlation part, but they do not tackle the missing data scenario. And most of these methods, from our knowledge, were not amenable to online settings also. And of course, there is a lot of dependency on parameter tuning. For example, you need to know the rank of the matrix, or you need to know the hyperparameters. But in our case, we really know nothing. We don't, you know, for all we know, the data may be high rank. Okay, so it basically gave us something to work with, and something to, you know, something to obviously, as researchers, we like our problem, new problems, and we were happy that the problem that we are posing cannot be solved to a good performance level, at least to our satisfaction by the methods that are already there. And we thought of what can be done. So basically, you know, we still applied the low rank uh, structure here, but we made a certain amendments. Now let me stop here and talk about, you know, why are we talking about Bayesian filtering? Okay, so a lot of work in ML and AI in recent years have used generative models. And by generative models, I mean, basically you have observation and you try to model the observation in a probabilistic sense. You try to fit a probability distribution to the data that you observe. Okay, and when you want to fit the probability distribution to the data, you essentially want to estimate the parameters of the probability distribution. So that's an inference problem. Okay, and it has been extremely successful, especially in last 5 to 10 years, especially in the deep learning framework. The generative models have given a lot of exciting avenues for research. So we thought of using generative model, except that we wanted to bring in the specificities of the current problem. So there are two specificities really. One is, you can see on the right side of your screen, this is my data Y. The Y spaces, the white spaces are the missing data, and the colored spaces are the other data that is available. Obviously, I want to complete the missing data. Okay, so these missing data, for example, could be a traffic information or could be air quality information. Now I'm saying that this Y can be written as a product of A and B, where A is a low rank matrix. In this case, rank is 2, and B is of course the coefficient corresponding to this rank. So if I know A and B, I can multiply A and B, I can get a Y hat, and that Y hat will contain the remaining entries that Y doesn't have. Okay, so this is the idea. If I know A and B. Okay, so that's the setup. The second setup is that because I'm claiming that the columns are coming sequentially, and the two columns that are near to each other, the two successive columns, have a relation in them because they are varying very slowly. So we thought of putting the state space model in the columns of B. So B is nothing but the coefficients corresponding to the subspace. Okay, and we are saying that, look, because the data is changing slowly with time, therefore the previous coefficient should be related with the current coefficient. This basically is coming from equation number 2 here. We are saying that B of tau is linearly dependent on B of tau minus 1 with this factor J. So J is a matrix. So B of tau is J of B tau minus 1 plus some noise. Okay, so this is the state space model on the coefficients of B. All right, so this is the extra innovation that we produced. Then we said that, look, Y is basically coming from A and B, and A and B are basically some random variables that, you know, that follow a certain distribution. So what all we want to do is, given equation number 2 and given Y is A into B, given these two factors, I want to find that A and B that fits my data to the best. Okay, so this is my subspace filtering approach. Okay, it's a very standard approach in statistical signal processing. So what are the key ideas? Well, the key ideas are 3 really. First, create a probabilistic subspace model taking temporal variation into account. So all I'm trying to say is that A and B are basically now random variables, such that the columns of B are dependent on the previous columns by equation number 2. Okay, they are random variables. Now I don't know their distributions. We are going to learn their distributions. Okay. Secondly, we observe the sequential but incomplete data, and then we approximate the posterior distribution of the model parameters. Basically, you know, it's a the standard practice, right? So you observe something, and based on your observation, you infer something. Okay, in our case, we observe incomplete data, we observe incomplete traffic data, we observe incomplete air quality data, and from that observation, we infer what are the best possible values of A and B. Okay, by coming to the posterior distribution of the model.
Pravesh, we only have a few more minutes left.
Sure,
so.
I think I'll finish in 3-4 minutes. Yeah. So that's it. So this is the idea, and the idea is standard. It's a standard signal processing approach where we want to find the posterior distribution of my parameters theta given the observation, except that I don't have py, I don't have the closed form expression of the density of the data, and therefore we don't go through py route. We find that density q star, okay, which basically approximates my posterior density to the best possible way. So we observe something, we observe y, we find that a and b using this model, and without going into the details of it, we basically, in our case, we applied what we call as mean field distribution approach, where we observed y of omega and we inferred a, b, j, and other hyperparameters that are important. I'm not going into details here for the lack of time. We simply observed and estimated the best possible a, and b, and j. So you can see, right? So these are the 3 key parameters, a, b, and j. And once we know a and b, once I know a and b, I multiply a and b and I get the remaining data. So I'll quickly go to the results. So this is the left side is, so how do, the one question is, how did we get, I said that there's no ground truth. So what we did was we first wanted to understand whether the model is true or not, whether the low rank model is true or not. So we got some China data. So China has a city which had 500, I think it's Shanghai. It had 500, or Shenzhen, either of them. I'm sorry, I'm missing the name. 450 monitors, around 400 odd monitors in a city. So we basically took their air quality data and we missed some of the data. So it's just a 25% data out of the whole data here on the right side. And then we completed using our approach the remaining data. Okay, so then we could see that with just 20 to 25% of monitors, we could get an error of almost 5 to 10% accuracy, which basically means that we don't need all the data. We have to simply move the monitors. Similarly, for traffic also, this is a traffic data. This is a traffic heat map, and A, B, and E, and H are basically the missing data, 25%, 50%, and 75%. And we could basically fill the remaining data by an approach of Bayesian filtering. So that's the main result. What is the takeaway? What is the takeaway of this talk? The takeaway is that you don't have to go first. First is that you have to look for what is the structure of your data, and there are many models that are already available. If you have the structured data, you just impose that structure in those models. You don't have to go to deep learning for everything. There are some nice non-deep learning models that are available also that may work in at least in our cases. At least it worked. And thirdly, you can, the most important conclusion that we drew is that you can actually monitor air quality of a city with very, very few static monitors, and actually a combination of static monitors and very few moving monitors, and still get the same air quality data, which basically means that we can employ such a service of putting monitors in public transit or in autos and actually measure a very dense map of air quality. So I guess I'll stop here.
Okay, thanks, Pravesh. I see, yeah, you had some more slides, but we are out of time. So 1 or 2 questions. One person is asking, can this problem be compared to signal reconstruction, as in compressive sensing? Is that comparable?
Indeed. So compressed sensing has been applied to traffic monitoring, in fact. And the idea is similar, that you have to look for a space where the data is sparse. But the difference there is that you have to find an over-complete space. I don't have a view of how good the performance is, but I suspect that it does not employ all the structure that is available with the data. So it may not do as good as what we're doing. That's my suspicion, but yeah, you can do that actually.
Okay, I think we are over time, so I think we'll stop the questions here, but you can maybe answer a few more if you have time on the type,
Absolutely.
the Q&A tab.
Yeah, I'll do that.
Thanks, Pravesh.
Thank you.
So that concludes our second session for the day. And maybe do you want me to launch the air quality polling in the background?
Actually, I do.
Okay.
Yeah.
So there's another poll he wanted you to answer, so I just launched it in the background. So now we'll have a few more poster presentations we will share. And after that, Nandan will take over for the final session of the day. We have two excellent speakers coming up, so do not go anywhere. We'll start sharp at 5:30 with those sessions. And meanwhile, I'll share a link for a feedback form for the overall summit. So if you could take some time and complete this feedback form, you can do it even after the sessions are over. But I would just like to paste it here so that you can save it and use it later. Pravesh, if you can stop sharing your screen, then Swagatika can. Yeah, Swagatika, you want to share?
Hello everyone, this is Amish, and in this video I will present Hello everyone, this is Amish, and in this video I will present So current deep learning models are deep-rooted in correlation-based methods. So explainability and interpretability of these models requires us to answer these following questions. That is, why did the model miss the prediction? When can we trust the model, and when the model fail? How can we correct the errors? We will be presenting two different frameworks for understanding why and when can the framework involves three different pipelines, and each of them, first one is like extracting internal concepts, that's like equation maximization. Second is flow-based instance, private concept iteration. So in one framework, we extract the visual concepts, human interpretable concepts from the weights of the network, and then try to convey the graph on top of that, and then extract the visual traits so that we can make interpretable nodes on the traits. Here are some results on brain segmentation model. Unit kind of architecture, you take on brain data. So this is the kind of results for equation maximization. This is the results for network dissection. So here we can see that network is learning some sort of implicit and explicit features, which is interesting. And this is the concepts obtained as a result of concept identification, where you can see local and global features. And these are traits which are used as a result of Venn framework. So we have these visual descriptions, visual features, as well as a description. Thank you.
Okay, Geeta, I have one more video to share.
Go ahead.